Introduction.
What are you doing, Amit?
I'm writing numbers.
Oh, natural numbers. Do you know what will we call the numbers if I add 0 with these?
Yes, I know. These are whole numbers now.
And what are these?
Negative numbers.
Yes, these are negative numbers. And the collection of all these numbers is called integers.
Interesting.
Do you know there are numbers like rational numbers and irrational numbers as well?
What are those?
Come, let's learn about them.
Objectives. At the end of this lesson, you will be able to define integers, rational numbers, and irrational numbers. Locate irrational number on the number line. Find the decimal expansion of real numbers. Represent real numbers on the number line. Add, subtract, multiply, and divide the real numbers, and state laws of exponents for real numbers. Numbers on number line. On a number line, numbers 1, 2, 3, 4, and so on are called natural numbers. The natural numbers are denoted by the symbol n. If we include the number 0 with the natural number, then the numbers are called whole numbers. The whole numbers are denoted by the symbol w. All these numbers together with these negative numbers are called integers. The integers are denoted by symbol z. Rational numbers. Now if we see between the numbers 0 and 1 or 1 and 2, we will see numbers like 1 by 4, 3 by 4 and so on. The collection of these numbers is called rational numbers. Rational numbers are denoted by the symbol q. Example. Let's now learn how to find rational numbers between the two given numbers. The given numbers here are 1 and 2. Say 1 is r and 2 is s. To find the rational numbers between r and s, we have to add r and s and divide the sum by 2. So we get 1 plus 2 is equal to 3 by 2. Therefore, the rational number between 1 and 2 is 3 by 2. Similarly, the rational number between 1 and 3 by 2 is 5 by 4. Assessment. Before proceeding further, let us know how much you have learned. Click true or false. Irrational numbers. You must be wondering if there are such numbers which are not in the form of p by q. Yes, there are numbers which cannot be written in the form p by q. Those numbers are called irrational numbers. For example, square root 2, square root 3, square root 7, 0.10, 1110, 1110, 11110, so on, pi and so on. If we collect all the rational numbers and irrational numbers and put them in a bag, then there will be no number left on the number line. And we call this collection as real numbers. Therefore, a real number is either rational or irrational. Irrational numbers on number line 1. Now we will learn to locate irrational number on a number line. Let us see where square root 2 is located on a number line. For this, we will firstly consider a unit square OABC with each side 1 unit in length. Now by using the Pythagoras theorem, OB square is equal to 1 square plus 1 square, or OB is equal to square root of 1 square plus 1 square, which is equal to square root of 2. To irrational numbers on number line 2. Similarly, to locate square root of 3 on the number line, we will construct BD of unit length perpendicular to OB. Then by Pythagoras theorem, OD is equal to square root of under root 2 square plus 1 square, which is equal to square root of 3. Now, by using the compass with center O and radius OD, we will draw an arc intersecting the number line at point Q. The point Q corresponds to square root of 3 on the number line. Assessment. Before proceeding further, let us know how much you have learned. Click true or false. Decimal expansion of real numbers. We have learnt about the real numbers. Now we will look at the decimal expansion of real numbers. By this expansion, we can distinguish between rationals and irrationals. Let us first take rational numbers. We will find the decimal expansion of these three numbers. Here we can see that on decimal expansion, the 10 by 3. Here we can see that on decimal expansion of 10 by 3, we get remainders 1, 1, 1, 1, 1. Similarly, the decimal expansion of 7 by 8 gives remainders 6, 4, 0. And remainder of 1 by 7 is 3, 2, 6, 4, 5, 1. Decimal expansion of real numbers too. Did you notice something here in all these examples? Notice that here the remainders either becomes 0 after certain stage or starts repeating itself. Let us go through these cases one by one. Case 1 is if the remainder becomes 0, then the decimal expansion ends after finite number of steps. The decimal expansion of such numbers is terminating. Case 2 is if the remainder never becomes 0 or repeats itself, then the decimal expansion of such numbers is non-terminating recurring. Example. Let us now have a look at one example. 1 by 3 is a rational number. The decimal expansion of 1 by 3 is 0.3, 3, 3, 3, and so on. And we can see that 3 is repeating here. We write it as 0.3 bar. Let's take another example. Decimal expansion of 1 by 7 is 0.142857, 1428557, and so on. Here 142857 is repeating. So we can write it as 0.142857 bar. Hence, if a number is rational, then its decimal expansion can either be terminating or non-terminating recurring. In other words, if the decimal expansion of any number is terminating or non-terminating recurring, then the number is rational number. And what do we call the numbers whose decimal expansion is non-terminating, non-recurring? Those numbers are irrational numbers. For example, square root of 2, pi, etc. Representation of real number on number line. We now know that every real number has a decimal expansion. That decimal expansion helps us to locate it on a number line. Let us locate 2.665 on a number line. We know that it lies somewhere between 2 and 3. Imagine to divide it into 10 equal parts. For clear view of numbers, now the first part represents 2.1 and the second part is 2.2 and so on. Here 2.66 lies between 2.6 and 2.7. Now focus on the portion between 2.6 and 2.7. Divide this again into 10 equal parts. The first part represents 2.61, the next 2.62 and so on. Again, 2.665 lies between 2.66 and 2.67. Let us focus on this portion of line and imagine dividing the portion into 10 equal parts. The first part represents 2.661, the second part represents 2.662, and so on. 2.665 is the fifth mark in these subdivisions. This process of visualization of representation of numbers on number line is called process of successive magnification. Assessment. Now answer the given questions. Click the correct option. Operations on real numbers. Can you tell what do we get if we add, subtract, multiply, or divide two rational numbers? We will get a rational number. But if we add, subtract, multiply, or divide the irrational numbers, the number we get is not always irrational. Now think, what do we get if we add or multiply a rational number with irrational number? The answer we get is an irrational number. Let us go through some examples now. Examples. Let's add 2 square root 2 plus 5 square root 3 and square root 2 minus 3 square root 3. We can write it in this way also. Hence, the answer we get is 3 square root 2 plus 2 square root 3. Let's now divide 8 square root 15 by 2 square root 3. We will write it in this way. We can write 8 square root of 15 as the product of 8 square root of the 3 and the square root of 5. Hence, the answer we get is 4 square root of 5. So from these examples, we can conclude that the sum or differences of a rational number with an irrational number is irrational, and the product or quotient of a non-zero rational number with an irrational number is irrational. Assessment. Let us know how much you have learned. Click the correct option. Identities. Now let us go through some identities related to square root. Let a and b be two positive real numbers. Then square root of ab is equal to square root of a into square root of b. Square root of a divided by b is equal to square root of a divided by square root of b. Square root of a plus square root of b multiplied by square root of a minus square root of b gives a minus b. A plus square root of b multiplied by a minus square root of b gives a square minus b. Square root of a plus square root of b into square root of c plus square root of d is equal to square root of ac plus square root of ad plus square root of bc plus square root of bd. Square root of a plus square root of b whole square is equal to a plus 2 square root of ab plus b. We can use these identities to solve many expressions. Rationalizing the denominator. Now look at this number. It is difficult to tell its position on the number line, but if we can rationalize the denominator, that is, make the denominator a rational number, then we can easily tell its position on the number line. So let us learn to rationalize the denominator. Here, since square root of 2 is irrational, so if we multiply it by itself, it will become rational. So, to rationalize, we multiply 1 by square root of 2 by square root of 2 by square root of 2, because this is equal to 1. Therefore, 1 by square root of 2 is equal to square root of 2 by 2. Now it is easy to locate 1 by square root of 2 on a number line. It is halfway between 0 and under root 2. Laws of exponents for real numbers. Remember the given laws of exponents. Here a is called the base and m and n are the exponents. Now guess what is a raised to the power 0? Yes, a raised to the power 0 is 1. Now let a greater than 0 be a positive number and p and q be rational numbers, then we can say that in multiplication, when bases are same, powers are added. In multiplication, two powers of the same base gets multiplied. In division, when bases are same, powers get subtracted. And when powers are same and bases are different and are getting multiplied, then we take the power as common. Examples. Now let's solve some examples using these identities. Let's simplify first one. 3 raised to the power 1 by 5 whole raised to the power 4. By multiplying 1 by 5 by 4, we get 4 by 5. So its answer is 3 raised to the power 4 by 5. Now look at second example. 13 raised to the power 1 by 5 multiplied by 17 raised to the power 1 by 5 is equal to 13 multiplied by 17 whole raised to the power 1 by 5, which is equal to 221 raised to the power 1 by 5. Assessment. Let's go through an interactivity now. Click the correct option. Did you know? The Pythagoreans in Greece, followers of the famous mathematician and philosopher Pythagoras, were the first to discover the numbers which were not rationals around 400 BC. These numbers are called irrational numbers. The Greek genius Archimedes was the first to compute digits in the decimal expansion of pi. He showed 3.140845 is smaller than pi is smaller than 3.142857. Aryabhat, 476 to 550 AD, the great Indian mathematician and astronomer, found the value of pi correct to 4 decimal places, 3.1416. Using high-speed computers and advanced algorithms, pi has been computed to over 1.24 trillion decimal places. Summary. Let us summarize what we have learned. A number is called a rational number if it can be written in p upon q form, where p and q are integers and q is not equal to 0. A number is called an irrational number if it cannot be written in p upon q form, where p and q are integers and q is not equal to 0. The decimal expansion of a rational number is either terminating or non-terminating recurring. The decimal expansion of an irrational number is non-terminating non-recurring. The real numbers are the collection of all rational and irrational numbers. For positive real numbers a and b, the following identities hold. To rationalize a denominator of 1 upon under root a plus b, we multiply this by under root a minus b whole upon under root a minus b, where a and b are integers. Let a is greater than 0, be a real positive number, and p and q be rational numbers, then